a chronicle of the motion of the heavens and the nature of things. In the year of our Lord, whilst the world is veiled in mysteries both divine and natural, I, humble servant of knowledge and of God's wondrous creation, do set quill to parchment, desirous to uncover the hidden order of the cosmos. Let this chronicle serve as a testament to the minds who, guided by reason and awe, sought to understand the motions of the stars, the fall of stones, and the very breath of the wind. Long before my own days, in the lands of ancient Greece, where marble columns rose like fingers pointing to heaven, there lived men of great pondering. Among them was Aristotle, born in the city of Stagira. He did propose in his wisdom that all things seek their natural place. Stones fall to earth, for they belong there. Fire rises, for it is akin to the stars. He spake of motion and of causes, and though he erred in some particulars, his words became the foundation of thought for centuries hence. The earth, he claimed, stood unmoved at the center of the universe, with the stars affixed to crystal spheres that turned in divine perfection. This was pleasing to the Church, for it set man at the center of God's creation, and so Aristotle's voice echoed through monasteries and cloisters alike, preserved by scholars of both Christendom and the noble lands of Islam. Yet truth is a flame that flickers in many hearts, and in the golden courts of Baghdad, men such as Al-Hazan, may peace be upon him, did take up the lens and study light. He questioned the old doctrines and, through careful experiment, began to see with eyes unclouded by dogma. Thus was born the seed of a new method: observation, test, and proof. In later years, a man called Roger Bacon, an English friar like myself, did write of such things with fervent hope. Experiment, quoth he, is the only safe guide in such inquiries. Oh, how I envy his clarity! And now, in these present days of the 14th century, I too perceive stirrings of a new age. The stars no longer seem so fixed, and whispers reach my ears of a Polish man, Nicholas Copernicus, who claims the sun, not the earth, sits at the center of all. Heresy, some might say, but wonder fills my soul. Thus begins my tale, of motion, of heavens, of the search for the laws that govern God's vast creation. If the Lord has written his design in the fabric of the universe, then perhaps, just perhaps, it is through the language of nature that we shall read his mind. Of revolt against the spheres, word hath reached even the shadowed cloisters of our libraries. Whispers born on the tongues of merchants and translated scrolls from the east. The heavens, they say, are not immutable. The stars do not wheel in perfect harmony. A great trembling now stirs the firmament not of the sky above, but of the ideas that bind our understanding to the ancient masters. I did not believe it at first. But then came the name Nicholas Copernicus, a quiet canon from the northern lands of Poland. He was no orator, nor seeker of glory, but a man possessed by numbers, instruments, and the unsettling simplicity of a sun-centered cosmos. He dared to write De Revolutionibus Orbium Coelestium, though not until the final year of his life, as though fearing the storm his quill would summon. In his reckoning, it was the earth that moved, rotating like a potter's wheel, revolving round the sun as if it were but one of many celestial pilgrims. At first I scoffed. To move the earth itself, madness. And yet, the elegance of his system, the symmetry of its dance, struck a deep chord in my heart. This was no heresy born of pride, but a vision forged in patient thought. Yet no idea is born alone. From the Germanic lands arose Johannes Kepler, eyes alight with feverish intensity. He was no mere follower of Copernicus, but a visionary who turned circles into ellipses. With trembling hands and the data of Tycho Brahe, a Dane who charted the skies without peer, Kepler uncovered the secret laws of planetary motion, not from divine revelation, but from geometry itself. "The orbit of Mars is not a circle," he cried, "but an ellipse." And with that, the perfect circles of Aristotle began to crumble, but none stirred more awe or dread than the man from Pisa, Galileo Galilei, a craftsman of telescopes, a breaker of illusions. With his own eyes he saw the moons of Jupiter orbiting not the Earth, but their distant lord. He watched the phases of Venus shift as if the heavens themselves confessed to Copernicus's truth. The church trembled. Galileo, bold as David before Goliath, declared that nature was written in the language of mathematics. That observation triumphed over authority. He dropped spheres from the Tower of Pisa, charted their fall, and found that speed grew with the square of time, a truth no parchment of Aristotle could contest. His enemies rose in robes and mitres, for such truths were dangerous. At Rome, under threat of inquisition, Galileo was made to kneel, and yet he is said to have whispered, "It moves." Thus the cosmos shifted not in the heavens, but in the minds of men. The ancient order cracked. From this fracture, a new world would be born. But I sense this is only the beginning. Beyond the mountains, a storm gathers. A man is coming, solitary, silent, and destined to shake not just the heavens, but the very core of existence. His name, Isaac Newton, of the man who commanded the apple to speak. When the old stars fell silent, and the heavens no longer turned for man alone, there arose from the mist-wrapped Isle of England a figure of such stillness, such cold, piercing clarity, that even the chaos of the universe seemed to yield before him. Isaac Newton. He was no court philosopher, no wandering sage preaching in the marketplace. He spoke little, avoided crowds, and lived more among books and calculations than among men. But in the solitude of his study in Woolsthorpe, while the plague ravaged London and emptied the universities, he beheld with a mind of unparalleled sharpness the order hidden beneath all things. It is said, though some dispute it, that the fall of an apple set his thoughts in motion. Why should the moon not fall as the apple falls, he wondered. And from that simple question grew a theory that would bind together the heavens and the earth. He called it universal gravitation, not a force dictated by angels pushing spheres on crystalline tracks, but a law predictable, measurable, mathematical, that governed all matter, from the grain of sand beneath one's feet to the orbs that wheel above. But Newton did not stop there. He tamed motion itself with his three laws, which even now I can scarce believe sprang from a mortal mind, that a body remains at rest or in motion unless acted upon. That force equals mass times acceleration, that for every action, an equal and opposite reaction must follow. These truths seem as eternal as Scripture, and yet they were born not in a holy book, but in the silence of his chamber. He crafted a new kind of science, mechanical, precise, obedient to calculation. The Principia Mathematica, his great work, did more than describe nature. It unveiled its mechanism. The planets no longer danced to the music of the spheres. They obeyed equations. The universe was becoming a clock, and Newton held the key. But not all rejoiced. Gottfried Wilhelm Leibniz, philosopher of the continent, brilliant and proud, challenged Newton's calculus, claiming he, too, had discovered that mysterious mathematics. Their followers quarreled bitterly, and the feud split Europe for decades. Yet in their rivalry, truth sharpened itself against truth. And still others spoke. Christian Huygens, a Dutch master of lenses, studied light not as Newton did, as a stream of particles, but as a wave spreading through the ether like ripples across a still pond. He built the first pendulum clocks and studied centrifugal force, finding laws where once there was only guesswork. The age of natural philosophy was transforming into physics, and the language of nature was no longer poetry, but mathematics. Men now debated the properties of vacuums, of pressure, of light, heat, magnetism, and electricity. No longer did they bow to the ancients for answers. They built instruments, performed experiments, and published their findings with trembling pride. Robert Boyle, nobleman and chemist, shattered the old notion of the four elements. Air, he proved, was not empty, but full of substance and law. He spoke of atoms, tiny, indivisible particles, as the building blocks of all matter. A vision older than Democritus, reborn in the crucible of reason. The Royal Society of London and the Académie des Sciences in France became new temples, not of prayer, but of observation. Their motto, nullius in verba, take nobody's word for it. Even kings now listen to their scholars. And yet, despite all this glory, the universe began to feel cold, mechanical, deterministic. If Newton's laws governed all, then where was the hand of God? Some, like Newton himself, believed the Lord must occasionally intervene to keep the machine running smoothly. Others, such as Pierre-Simon Laplace, a century hence would claim that given all positions and velocities of the particles in the universe, one might predict all things, past and future. No miracles needed. "Where is God in your system?" Napoleon once asked him. "Sire," Laplace replied, "I had no need of that hypothesis." And so the age of wonder marched into the age of certainty. But certainty is a fragile thing. Far beyond the grasp of these clockmakers, at the very edge of vision, light behaved strangely. Heat flowed mysteriously. Electricity and magnetism danced in unpredictable harmony. A new storm was brewing. And soon another kind of thinker would arise, not of divine simplicity, but of paradox and complexity. The world would once again be broken open, not by gravity, but by light itself, of sparks, engines, and invisible threads. Though Newton's shadow loomed long over the world, it did not halt the minds of men from prying deeper into the fabric of creation. The universe, now a vast machine, ticked with elegance, but beneath its polished gears, new murmurs stirred. Whispers of fire that could move engines, of metals that attracted without touch, of forces unseen, yet terribly real. The age of reason had built its temples. Now came the age of experiment. It began with heat. James Watt, a Scotsman of clever hands and sleepless nights, took the clumsy, hissing engines of coal mines and breathed into them purpose. His improved steam engine, born of condensation and cunning, did more than lift water. It powered factories, ships, and the dreams of empires. The age of motion, once ruled by falling apples and celestial orbits, now belonged to pistons, pressure, and progress. But no one yet understood why heat made things move. What was heat? Was it a substance like phlogiston, as some proposed, or a motion of particles, as others dared to think? Then arose Sadi Carnot, a Frenchman with the mind of a soldier and the soul of a philosopher. In his brief, luminous life, he asked a question no one had asked clearly before. What is the most efficient way to convert heat into work? His answer, though born before the full understanding of energy, would one day become the cornerstone of thermodynamics. Energy, it seemed, was eternal. Not created, not destroyed, only transformed. This law, whispered first by Joule and Mayer, would spread like fire through every corner of science. A new principle stood beside Newton's gravity. Conservation of energy, a law as iron-bound as any scripture. And still deeper forces called. Electricity, that ancient curiosity which once made amber attract straw and fish, twitch upon metallic hooks, now revealed itself as a great river flowing through all things. In the salons and workshops of Europe, bold men captured it in wires and jars. Luigi Galvani, by accident or providence, made the legs of a dead frog dance with the touch of metal. From this grotesque miracle, Alessandro Volta built the first battery, a stack of discs that summoned forth a steady stream of power, like lightning tamed. But it was Michael Faraday, son of a blacksmith and apprentice to a bookbinder, who changed the world. He was no mathematician. He spoke softly, humbly, and with awe. Yet in his humble laboratory, he turned magnetism into electricity and electricity into motion. He discovered that a moving magnetic field could induce an electric current, and thus invented the principle behind all modern motors and generators. What Newton did for the heavens, Faraday did for the invisible world. His lines of force, drawn with care and reverence, were scoffed at by his learned peers. "Where is the equation?" they asked. But another man answered. James Clerk Maxwell, a Scotsman with a poet's heart and a mind that burned like crystal, took Faraday's lines and translated them into 4 majestic equations. These, more than any sword or treaty, united the world. Electricity and magnetism were not separate forces, they were one. And light was not merely a beam or a wave, but a ripple in the electromagnetic field, a vibration in the very stuff of space. The ether, they said, must exist, a subtle medium through which light waves travel. How else could a wave exist without a sea? And yet, when Michelson and Morley built their delicate device to detect the Earth's motion through this ether, they found nothing, no drift, no resistance, as if the ether did not exist at all. Confusion set in, a crack formed in the great edifice. Maxwell's equations could not be denied, but how could they be reconciled with Newton's absolute space and time? Then, from the quiet corners of the 20th century, arose a man unlike any other. His hair unkempt, his manner strange, his eyes always distant, as though gazing upon a truth others could not bear. Albert Einstein, time bent and atoms shattered. He was no child of privilege, a patent clerk in Bern, unknown, overlooked, a mere whisper in the halls of academia. But in the year of our Lord 1905, Annus Mirabilis Einstein published 4 papers that would rip the veil from reality itself. He showed that light, under certain conditions, behaved not only as a wave, but as a particle, a quantum of energy. This explained the photoelectric effect and opened the door to a new and terrifying world. He proved that Brownian motion, the jittering of dust in water, was the echo of invisible molecules colliding. The atom, once a philosophical ghost, was now real, proven by mathematics and microscope alike. And then, most wondrous, most heretical, he rewrote space and time. In his special theory of relativity, he claimed that the speed of light was not altered by motion, that time itself slowed for the fast, and that mass and energy were one and the same. EEMC2, a mere equation, yet heavy as the stars. The old absolutes time, space, simultaneity dissolved. And 10 years later, in his general theory, Einstein bent gravity itself. No longer a force, it was the shape of space, the curve of time caused by mass. The Earth did not fall toward the sun, it rolled along the contours of a warped cosmos. The philosophers reeled, the mathematicians wept, the priests wondered if they had seen the face of God. And yet even Einstein, with all his fire, could not stem the tide of uncertainty. In laboratories around the world, strange phenomena emerged. Electrons did not follow paths, they leapt. Light split and interfered with itself. Observation seemed to change reality. A new breed of physicists arose, Heisenberg, Bohr, Schrödinger, and they declared a universe not of certainty, but of probability. A cat, they joked grimly, could be both dead and alive until observed. The age of classical physics was dead. In its place stood the quantum world, a world of shadows, glimpses, contradictions. A world where cause did not always lead to effect, where the very act of measurement shaped the outcome. And still the chronicle is not done. For beneath the quantum realm, deeper mysteries lie. Strings may vibrate in dimensions we cannot perceive. Black holes may hold secrets beyond the veil of time. And somewhere, perhaps, at the edge of reason itself, the final law awaits discovery. But that, dear reader, is a tale for another night. Particles, colliders, and the symphony beneath silence. After Einstein, the world stood stunned. The certainties of centuries had vanished like mist, and in their place came ambiguity, beauty, and fear. Men now knew that nature was not made for comfort, nor its truths designed to soothe. It was the age of quantum mechanics. Werner Heisenberg, barely in his 20s, grasped what few dared: that we cannot know both a particle's position and momentum at once. Not because our tools are clumsy, but because the universe itself refuses such certainty. His uncertainty principle was not a limitation of knowledge, but a law of existence. Then came Niels Bohr, sage of Copenhagen, who preached complementarity, that particles could behave as both wave and matter. That truth itself could wear many masks. In his orbit gathered a new brotherhood: Dirac, Born, Pauli, Fermi, Jordan, de Broglie. Each with their own vision, each chiseling reality from the granite of paradox. In smoky rooms and chalk-dusted halls, they argued, laughed, despaired. Erwin Schrödinger, poetic and restless, proposed a wave function, an ethereal, ghost-like thing that describes not where a particle is, but where it might be. His famous cat, trapped in a box with death and chance, became the symbol of a universe undecided until seen. But then came a challenge, not from within, but without. The atom, long thought indivisible, was split. First its electrons were understood, then its nucleus was cracked like a seed. Rutherford had called it mostly empty space. Now men sought to understand the fire within. Enrico Fermi, with hands both patient and deadly, began to probe the heart of the atom. His work led to chain reactions, taming the invisible power that once lit stars. In secret laboratories during the Second World War, physicists became alchemists, and their discoveries birthed the bomb. In 1945, at Trinity, the desert bloomed with fire brighter than the sun. And Oppenheimer, who had brought it forth, whispered ancient words: "Now I am become death, the destroyer of worlds." Physics had split its soul. One branch soared toward unification, seeking harmony in field equations and symmetries. The other crouched in bunkers, measuring megatons. Yet amid the ashes, the search continued. The universe, it seemed, was built not just from atoms, but from smaller, stranger entities: quarks, gluons, neutrinos, bosons. Particles with spin, color, charge properties not of form, but of interaction. These were not like stones or dust, but echoes in an invisible field, ripples in a quantum sea. And thus was born the Standard Model A theory, not of objects, but of forces and fields. It catalogued the known particles, from the up and down quarks that built protons and neutrons, to the photon, carrier of light, and the W and Z bosons, messengers of the weak force. Gluons stitched together quarks, neutrinos slipped ghost-like through matter, and somewhere, hidden, was the Higgs boson, the particle that gave mass to all the rest. For decades it was hunted, and then, in 2012, in the underground cathedral of the Large Hadron Collider, they saw it, a spike in the data, a resonance in the void. The Higgs boson prophesied, doubted, and finally seen. The crowd of physicists wept, and yet, even as champagne flowed in Geneva, unease spread. The Standard Model was beautiful, but incomplete. It said nothing of gravity, nothing of dark matter, which outweighs the stars fivefold, nothing of dark energy, which tears galaxies apart, nothing of the origin of the universe itself. Chapter 7, of strings, multiverses, and the fraying of reality. With their equations fraying, their models cracking, the physicists turned to a new hope, a theory older than many knew, but newly rekindled. String theory. What if, at the smallest scale, particles were not points, but vibrating strings, infinitesimal loops of energy, each vibrating at a different frequency, like notes on a cosmic harp? In this view, an electron is not a marble, but a melody. A graviton, a ghostly hypothetical quantum of gravity, might be just another note, but strings need space to vibrate. Not just our familiar 3 dimensions of space and 1 of time, but 10, or 11, or more. Dimensions curled upon themselves, tighter than atoms, invisible yet essential. Our universe, it seemed, might be a brain-one membrane among many, floating in a higher dimensional void. It was no longer physics, it was cosmology, philosophy, myth. Some theorists, Edward Witten, Juan Maldatena, Brian Greene, Lisa Randall wrote of M-theory, brain worlds, ad esse CFT duality, and the landscape of possible universes. Some spoke of a multiverse, not one universe, but many. Infinite, parallel, divergent. Every possibility played out somewhere, every choice made, every particle configuration existing somewhere in the great quantum foam. To others, it was madness. Even Einstein, before his death, recoiled from quantum indeterminacy. God does not play dice, he said, but the dice had already been thrown. And now, in the laboratories of today, physicists search for what lies beyond. They fire protons at near-light speeds. They cool atoms to a breath above absolute zero. They watch for gravitational waves from colliding black holes. They chart the polarization of the cosmic microwave background relic of the Big Bang, the firelight of the universe's birth. Some dream of a theory of everything, a single equation, elegant and final, that would unite quantum mechanics and general relativity, that would tell us not just how things move, but why there is anything to move at all. And perhaps, if we find it, we shall look back, past the super colliders and silicon chips, past Newton's apple, past Galileo's moons, past Aristotle's spheres, and see that the journey began with wonder, with a question whispered beneath candlelight, with a thought daring to ask, what moves the heavens? Epilogue of the fire that never dies. We are not finished. There are mysteries still. Questions that claw at the edge of reason. What is consciousness? What came before the Big Bang? Is the universe finite or infinite? Are we alone? The physicist now stands where the priest once stood, before the veil, staring into the dark. But unlike the old priest, the physicist dares to pull it back. This story is not yet ended. It is written still by hands in darkened observatories, in sterile labs, in the minds of children staring at the stars. And maybe one day a new name will be added to this chronicle, yours. Black holes, time's arrow, and the silence beyond the horizon. By the end of the 20th century, physicists had peeled back layer upon layer of reality. Yet beneath it all was a silence they could not explain. Gravity, that old monarch of the cosmos, remained defiant. Einstein had bent space and time into a single tapestry. He showed how massive objects curve it, how light itself bends beneath that curve. But as they peered deeper into Einstein's equations, they found something monstrous. Something he himself first uncovered and then rejected with trembling hand. Black holes. Places where gravity grows so dense, so concentrated that not even light may escape. Where time slows to a crawl and space folds into itself. At their center, the singularity, a place where all known laws break down, where density is infinite and meaning disintegrates. Einstein doubted they could exist. But Karl Schwarzschild, dying of disease in the trenches of the Great War, found their mathematical signature. And decades later, Roger Penrose and Stephen Hawking proved they were not fantasy, but inevitable woven into the fate of dying stars. Astronomers peered into the night and found them lurking at the hearts of galaxies, devouring matter, bending starlight, spinning space like a whirlpool. In 2019, the world saw the unseeable, a photograph captured with telescopes the size of Earth itself, of the shadow of a black hole, a ring of fire around an abyss. But still the mystery deepened. Hawking, wheelchair-bound but mind ablaze, showed that black holes are not entirely silent. They radiate. Slowly, imperceptibly, they evaporate. Over eons they shrink, fade and vanish. But where then does the information go? The details of what fell in stars, atoms, histories. This became the black hole information paradox, a war between quantum mechanics, which demands that information is never lost, and general relativity, which seems to swallow it forever. In that paradox, physicists saw a deeper truth, that to reconcile these two great theories, gravity and the quantum, they would need a revolution not of tools, but of thought. They turned to holography. What if all the information inside a black hole, or even inside the universe itself, was encoded not in its volume, but on its surface? What if reality as we experience it is but a projection? And thus was born the holographic principle, most clearly revealed in AD-SCFT correspondence, a strange duality where a theory of gravity in one world matches a theory of quantum fields in another. Different yet identical, two sides of a cosmic mirror. As above, so below. But the questions did not stop at black holes. They turned to time. Why does it move only forward? Why do eggs break but never unbreak? The equations of physics do not care forward and backward in time. They work just the same. But we and the universe we live in seem to march only one way, toward heat, disorder, decay. Entropy, that arrow of time, always rises. And yet, at the edge of a black hole, time itself stops, and at the birth of the universe, time may not have existed at all. We speak now of the Big Bang, that first instant, where all space and time exploded from a singularity. But what came before? Here, language fails. Some suggest a bounce, a previous universe collapsing, birthing this one. Others suggest an eternal multiverse, with bubble universes birthing endlessly in a quantum froth. Some dare whisper that time itself is an illusion, that all moments exist at once, and consciousness merely experiences them sequentially. And in the cold light of modern observation, one thing becomes clear: our universe is dying. Galaxies flee from each other faster and faster. A mysterious force, dark energy, pushes them apart. In time, stars will burn out, black holes will evaporate, and only cold, silent particles will remain. A great darkness, a heat death. But is that the end? Or the beginning of something deeper? Minds, machines, and the physics of the self. While physicists chased particles and galaxies, a new force awakened. The mind. What is consciousness? What is the self? Are we mere arrangements of atoms, dancing to deterministic laws? Or is there something more? Neuroscientists mapped the brain, neuron by neuron. Computer scientists built machines that think, learn, play. Artificial intelligence, once a fantasy, now shapes our words, our choices, even our wars. Some call it a tool, others call it a new species. But is consciousness computable? Roger Penrose again stepped forth with boldness. He argued that the mind cannot be simulated, that quantum processes in microtubules might explain awareness. Others, like Daniel Dennett, denied this. Consciousness, they said, is an illusion, a trick played by meat and memory. Still others turned to integrated information theory, proposing that consciousness is a measure of how parts of a system affect one another. A physics of subjectivity, and always the question lingers. If the laws of the universe gave rise to us beings who ask about the laws, then who or what are we? Are we observers or participants? In the many worlds interpretation of quantum mechanics, every decision spawns new realities. Every choice splits the cosmos. Somewhere you chose differently. Somewhere the stars never formed. Somewhere no one ever asked these questions. But in this world, here and now, we ask. And the asking matters. The future and the edge of the possible. The physics of the present is not settled. It is stormy, divided, alive. Some chase quantum gravity string theory, loop quantum gravity, causal sets, emergent spacetime. Others pursue quantum computing, building machines that process information not in bits, but in qubit superpositions of 1 and 0, entangled across space. Such machines may one day solve problems in minutes that would take the universe itself billions of years. Some dream of warp drives, wormholes, time machines, solutions buried deep in Einstein's equations, requiring negative energy and exotic matter. Others dream of simulations, that we are not real but data, that the universe itself is a computation, that behind the stars lies not a divine architect but code. And some look farther still, toward theory of everything, a final unification, a single principle, simple and inexorable, that gives rise to all else. Forces, fields, particles, time, life, beauty, sorrow. But even if such a theory is found, what then? Will it explain why there is something rather than nothing? Will it explain why the laws are as they are? Or must we accept that some things lie forever beyond reason, that in the end, physics brings us only to the gates of mystery? A candle in the vastness. This has been the story of physics, not merely a history, but a pilgrimage. From Aristotle's spheres to quantum fields, from stone towers to particle accelerators, from the gaze of shepherds to the dreams of machines. It is a tale not of certainty, but of daring, of minds who challenged the gods, who broke the chains of tradition, who risked madness for meaning. It is not over. Even now, new thinkers rise. Young minds read these chronicles and ask better questions. Perhaps the final chapter will be written not by Einstein, nor by string theorists, but by someone who reads this, someone who looks at the stars not with reverence, but with purpose. And perhaps, in the end, we shall find not just the laws of nature, but our place within them. Aliens, silence, and the shadow of other minds. For all our progress, for all our instruments scanning the sky, one mystery has deepened, not faded. Where is everyone? The universe is vast trillions of galaxies, countless planets. Life, we presume, should not be rare. And yet we hear only silence. This is the Fermi paradox. Explanations abound. Perhaps civilizations destroy themselves. Perhaps they transcend into forms we cannot detect. Perhaps we are early. Perhaps we are alone. Or perhaps reality is filtered. Some theorists suggest the simulation is limited. Its rendering focuses only where conscious agents observe. The stars beyond may be empty until we look. SETI listens. Telescopes watch. But perhaps the signal we seek is not out there, but embedded in the laws themselves, in the mathematical constants, in the structure of DNA, in the quantum noise. A signal from the architect. But if it exists, it may not speak in words. It may speak in symmetry, in beauty, in curiosity itself. Chapter 16, of Immortality and the Physics of Being. The questions now become personal. What is death in a physical world? If consciousness is process, not place, if identity is pattern, not particle, then what does it mean to end? Some seek answers in cryonics, hoping to preserve the body for an age when knowledge may resurrect it. Others invest in digital immortality, mind uploading, emulation, memory encoding. The mind, in theory, is data. But is that you? And if you could simulate a perfect copy of yourself, indistinguishable in thought and feeling, would you still be you? Quantum physics muddies the water further. In the many worlds view, death may be relative. You always awaken in the branch where you survive. Some call this quantum immortality, a theory both thrilling and terrifying. But physics offers no clear answer, only that we are structures of energy and pattern, brief configurations of entropy and order. A flame in the wind, yes, but one that burns with questions. If this journey through time, thought, and the fabric of reality has stirred your curiosity, then let it be only the beginning. Subscribe to the channel for more explorations into science, philosophy, and the edge of the known. New chapters await, and your presence makes the story richer. Thank you for watching. Stay curious and keep asking the big questions.